Hey everyone, you are watching the lesson for Unit 1, Lesson 2. This is going to cover just basic skills you need to know before we really jump into physics. So, share screen, and we're just going to go over this. So, your first assignment essentially is kind of like doing algebra, and then graphing. So, we're really just going to talk about that. And talk about algebra, all I'm really saying is knowing how to manipulate equations and formulas and things like that. So, for example, if we had, let's make sure, we could use the slope-intercept form, right? Hopefully, you guys have seen this before. I might ask you to solve for m, right? I'm not talking about solving for the slope. We're using y2 minus y1 over x2 minus x1. I'm just talking about specifically get this m by itself. What we're going to essentially do for this one is subtract b from both sides. We get y minus b equals mx, and then we're dividing by x on both sides. So that cancels one side out. We get y minus b, that equals m. So being able to manipulate, sometimes things can get a little complicated. So for example, this is one of the equations we'll be using eventually. It is the final squared equals the initial squared plus 2a change in x. Right? There's a lot there. We have subscripts. We have, this is another subscript, another exponent. We also have this thing called delta, right? And we want to be able to be comfortable with manipulating these equations. So for example, let's manipulate the initial velocity. This is our initial velocity. I spelled that wrong. Initial. By itself. So something that you can always keep in mind is that subscripts are just part of the variable. They're just there to kind of differentiate. So we have, for example, an f, a velocity final, and a velocity initial. They're different variables, but they're similar in that they're the same physical quantity. So what we're going to do is first we want to subtract all of that. So we get v final squared minus 2a change in x. And this change in x you can kind of group together as well. This is one number. So don't worry too much about that. That triangle really just means it's a delta. It means change in. So that means that if you're going from one place to another, what was your velocity when you started? What was your velocity when you ended? Right? And that all equals your initial velocity squared. Take a square root of the whole thing. So you get something that looks nice and messy. Right, square root over here. Right. So that kind of honestly looks a little scary, and you might be thinking that you want to drop this class now. But don't be afraid of it. It's really just using algebra rules in order to manipulate equations. Really thinking about it now, this equation right here, I'm not even sure if we're going to use it much. You might look at it, but you might not really use it too much. One that we will be using, though, is the average velocity equation. Average velocity equals your change in distance or your displacement over time. That one's much easier. Yeah, you still have subscripts going on. You still have this little delta guy right here. But if I asked you, for example, to solve for t, right, I would expect you to know how to do that. And just to do it one time. Usually the way we do that is cross multiply and then get t by itself. Have the average t equals change in x, and then finally we get t by itself. T equals change in x over the average. Right? And that would be kind of like your final answer. And then there might be a time where I ask you, hey, now your change in x is, say, 10. Your average velocity is 5. That, right? So it's 10 divided by 5. That gets us 2. Right. So there are ways of solving equations that are analytical. Right. It stems from the word analyze, right? And then there are other ways where we solve them that are numerical. right? So in terms of algebra, that's what I want you to know. When we do conversion factors, this is also very important. So now we're talking about conversion. And really, what we're alluding to is something called dimensional analysis. Analysis. I think that's right. Hope I spelled that right. So the basic, we have 1 meter, 15 meters. And I want to change that to kilometers. Usually what we do first is find a conversion factor. If you look it up on Google, you'll know that 1,000 meters equals 1 kilometer. And maybe if you are just used to doing these conversion factors, you'd really quickly just set it up. You maybe just move the zeros, whatever. But I want to go through the slow way, the way that always works, so that I can. So first off, we have these two guys, right? This equal sign right here, that means that these two sides are equal. So what I am going to want to do is I'm going to divide both sides by 1,000 meters. So I'll take this side. Right. On the left side here, these all just cancel out. Right? We don't get anymore. But they don't cancel out to 0. They cancel out to 1. So what we get really is 1 equals 1 kilometer over 1,000 meters. Cool. What this tells us is that since there's this equal sign here, that the number 1 is equal to this factor right here, 1 kilometer divided by 1,000 meters. Now we can't cancel the right side out because the units are technically different. But what this tells us, though, is that if we were to multiply this factor by anything else, it's the same as if we were just multiplying it by 1. A special kind of 1, I suppose, though, because it has units. So when we actually go to set up this equation, right, we have 15 kilometers, which is what we started with, multiplying by it should be 15 meters. That's my mistake. I'm getting ahead of myself. 15 meters times 1 kilometer over 1,000 meters. What's really happening here is we know that this factor right here, that's also equal to 1, right? So when we're doing dimensional analysis, when we're converting between units, we're really just multiplying by special conversion factors that really just represent the number 1, right? So when we change this, right, we get 15, and I'm not going to cancel out the units yet. We get 15 kilometers over meters divided by, so 15 over 1,000, right? Meter, kilometers over meters. If we divide 15 by 1,000, we just move the decimal place over 3 times, 1, 2, 3. So we get a 0.015 kilometer. Sorry, I keep almost jumping ahead of myself. 0.015. I'm not going to cancel the units yet. Meter, kilometers per meter. And this is a weird unit. You've probably never seen this before. The reason why I wanted to leave this is because I want to show you what the nature of units were like. You can treat units essentially as variables. So for example, if I had divided by x and I asked you to reduce that, you just get 1. If you had xy over x, we end up with y. Same thing here. We have m, km divided by m. These cancel out. So we're really just left with 0.015 kilometers. Right. So when you do conversion factors, really you're just multiplying by 1 in a special way where your units are different so that you can convert between units. So I always think that's important to know. The last thing I want to talk about is graphing, and this is going to probably be the longest portion of this. I just want to go through how you make a good graph. So let's a data table. Let's say we have a distance and really quickly, I'll just put some factors in. Let's say we start at 5, 8, 9, 0, can do 2, 4. So I'm gonna make a graph here. Table. We'll do a 5 by 5 just to make it simple. I need to redo this really quickly. Oh. Computer lagged a little bit, so we'll put it up here. So I'm gonna use this table as a representation of a graph, right? So we have a 5 by 5. It's okay that these are kind of long in length. We're just trying to prove a point. So first thing, if I have a distance versus time graph, that's definitely my title. Your title always tells you what is on the X and what is on the Y axis. So a title for scientific graphing is always going to be your Y versus your X. So make sure you always, if I ever give you a graph and I tell you it's going to be like an energy versus time graph. So we can actually write this down. I didn't give you units, so we're going to say this is meters. We're going to say this is seconds. If you're not comfortable with the metric system, that's all we're going to use basically the entire year. So learn to get comfortable. So we have distance here. It's measured in meters. Notice I have the units and the label. On the bottom we have time. Measured in seconds. Now it's about figuring out our scaling. There's a surefire way to figure out scaling. You can kind of eyeball it, but sometimes you're off. You have to make the graph longer, or sometimes you end up making like a really tiny graph that doesn't work out so well. The easiest way you can do this is you take the biggest number in both of your data tables. So we have 9 and 4, 9 meters, right? And we're going to divide by the number of boxes on your y-axis because this is our y variable. So we divide that by 5 boxes. We do 9 divided by 5. That gets us about 1.8. Our unit would be meters per box. And what that essentially means is that if I were to go up this graph 1.8 every single time, by the time I hit this top last one, I would get exactly 9. 1.8, however, kind of looks disgusting. Add by, so we're just going to round that up. You always need to round upwards. So we get 1.8. We can just say instead 2 meters per box. So then we can go ahead and label it. We have, of course, 0 at the bottom. 2, 4, 6, 8, 10. Sometimes my zeros look like 6s, so just be careful. Next, we do the other one. Divide by 5, and it's 4 meters per box. That gets us 0.8 meters per box. And again, we're going to round that up to 1 because that looks nice. My mistake, however, though, obviously, is this should be seconds. This should be seconds. This should be seconds. My mistake. So we go up. That's easy. We have 1, 2, 3, 4, and 5. Then we're going to go ahead and graph these. So we just have 3 data points. We have 1 at 0.5. We have 1 at 2.8. We have 1 at 4.9. And there's one last thing we need for this graph, which is the line of best fit. Your line of best fit does not ever have to start at the origin. You can start wherever you want, but when you're doing it, you want to definitely get as close as you can to the middle. So something like that looks pretty good. So now I'm just going to talk about this graph and what this graph really means. So let's scoot over here. There's 4 main parts we're going to talk about. We're going to talk about finding your slope. Talk about units of the slope. Then we're going to talk about what the slope means. And lastly, we're going to talk about using your line equation. Right, so again, you're not getting too much past Algebra 1 skills right here. So finding the slope, we just use the equation for it, y2 minus y1 over x2 minus x1. However, we need to find our points to use. As you can see, he's great here. This data point here and this data point here, they're not on your line of best fit, so we can't use them. This one right here, however, is. So what I'm going to do is I'm going to use this data point here, and this is also right on the intersection right there too. So we have our 2 points right there. Our point 1 being our closest one to the y-intercept, which is 0, 5. And our second one being 1, 6. Right, we're going to plug that in to our equation. So we get y2, which is 6, minus y1, which is 5, over 1 minus 0. That gets us 1 over 1, which essentially is just 1. So our slope tells us that for every 1 we go up, we go over 1 as well. So cool. Something else I might all this basically means is this. We're looking at a rate of change, right? So we look at the distance, it's measured in meters, time measured in seconds. Your slope is simply going to be measured in whatever your units are on the y-axis divided by your units on the x-axis. So our units on the y-axis are meters, units on the x-axis are seconds, and your units of the slope then is going to be a meter per second, right? This is a measurement of speed. Very similar to for example, a mile per hour, right? So the units of the slope are meters per second. So if we go and plug this actually back in, right here, our slope is actually 1 meter. So it goes up 1 meter for every 1 second. And that so far hopefully makes sense. Now talking about what the slope means. Usually when I ask students this question, they say it's your rise over run, or it's for how much you go up, you go over. But really what it means is the average. So if I were to ask you specifically what the slope meant, it would be the average. But it's not just the average, it's going to be your average speed. Your average speed. So for example, if you went on a trip, from Chicago to, say, Florida, right, you would go at various different speeds. Sometimes when you're in the highway, you might go an hour. When you're in the suburbs or you're passing through a city, you might go a little bit slower, right? So you'd be finding, right, the different, if you want to calculate your average speed, you'd record how fast you're going at every single point in time, and then you'd figure out the average, right? For this graph, what we have is how much distance was traveled, how much time has passed, and how much time has elapsed. It actually gives us, when we look at our slope, our average speed. So this graph specifically is average speed. We could also have a graph, for example. It could be energy measured in joules and time. So this is just an example, measured in seconds. If we were looking for, let's say we had a slope that looked like that, this line of best fit would give us average power, because a joule second is the same as a watt. Watt being, if you think about a light bulb, right? When we talk about wattage, it's how much energy a light bulb uses per second. So that's actually, technically speaking, where you get the equation for finding power. And we'll figure that out later when we go through the energy unit. But I just didn't want you to think that every line of best fit means average, whatever it's graphing. Finally, using your equation, we're just going to set it up. We know the line equation is y equals mx plus b. Our b's are y-intercept, so we simply go for graph, and we know that we use the data point 0, 5. So we know that our y-intercept is simply 5. So we just plug this in. We have y equals 1 meter per second. We don't need to put that in. Y equals x plus 5. If we want to be really specific, since we're doing physics, we would say 5 meters, right? Because Next, let's just propose a problem. So let's say, where is my mouse? There it is. I tell you that this graph right here, this was actually a graph for someone in a race. So maybe I want to know how much time has passed after he's gone 20 meters. So let's say, assuming the runner stays at the same average velocity or average speed, he has run 20 meters, how much time has elapsed or passed? So all we're going to really do with this one is we're just going to plug this 20 meters into whichever variable it corresponds to, and it corresponds to distance. We look, distance is our y-axis, so it's going to be a y variable. So we have 20m equals x plus 5 meters. Subtract that from both sides, we get 15 meters equals x, right? So one issue though is that it's not actually 15 meters, right? Get an eraser. It's really, you might be like, wait a second, if I subtract 5 meters from 20 meters, that gets me 15 meters. Something we can't forget about is that this actually had units too. So really, it was 20 meters equals 1 meter per second times x plus 5 meters. So if we were to do this again, get 15 meters equals 1 meter per second times x. Now, if we get that 1 to the other side, right, we're going to divide by 1. Get 15 meters over 1 meter per second. This s is going to go to the top because of algebra rules. These m's are going to cancel out. So what you're really left with then is 15 seconds equals your x. And your x obviously being your x-axis, which is a measurement of time. Was a lot. Algebra, we have conversion factors, dimensional analysis, and we have graphing. So feel free to, if you have questions, just send me some emails. If we meet on a Wednesday or a Thursday, whenever we decide, you can also ask questions then. You can also leave a comment on this video as well. So hopefully that wasn't too overwhelming. I really hope that a lot of this was just review for you guys, because to you freshman. Learn it again. For sure, look on YouTube, see if there's other sources. I'll try to link some too if I find any good ones. But that's it for today. Thanks. Have a good day.